systems in several variables. Even though this section is entitled Systems in Several Variables, we're going to stick with just 3. And we're going to solve a system of 3 equations with 3 variables. This requires a lot of patience, a lot of rechecking every step, and we're going to use the process of elimination. Or addition, some books call it addition. And you can use substitution to do these, but it usually ends up much messier. So what you do is you decide to get rid of a particular variable, any of the 3 that you choose, and that's fine. So I'm going to choose to get rid of the x's from the top 2 equations because that doesn't require any multiplication or anything. If I add those, I'll just be able to get rid of the x's right away. So I'll recopy those 2 equations. And we add those together. So when you add them, the x's cancel, and we end up with just 1y minus 3z equals 5. After everything I write down, I check and make sure, first of all, that I've copied everything correctly. And then after every operation I perform, I go back and double check and make sure I've done that correctly. There are so many places to make mistakes on these, and one little mistake is going to ruin an entire page worth of work. Now, because I got rid of the x's just now, I'm going to put 2 different equations together, and I also have to get rid of the x's. Whatever you get rid of the first time, you have to get rid of the second time. So I'm going to choose the middle and bottom equations. Have to get rid of the x's because that's what I just got rid of the first time. So for my x's to cancel, I would have to multiply all of that middle equation by 2 so that I have a negative 2x to cancel with my positive 2x. Multiplying everything in the middle equation by 2 would give me negative 2x plus 8y minus 8z equals 2. And then the bottom equation I can just leave alone. And I add. The x's go away. I'm left with 7y minus 3z equals negative 1. Now I have 2 equations with 2 variables, both y and z. Y minus 3z equals 5. 7y minus 3z equals negative 1. So I'm going to put those 2 smaller equations together, and I have to decide if I want to get rid of the y's or the z's. Since the z's already have 3's in front of them, I'm going to choose z's. But one has to be positive and one has to be negative. So I'm going to multiply the y minus 3z equals 5 equation, everything by negative 1, so that I can make my z's cancel out. So now I've got negative y plus 3z equals negative 5. And then the 7y equation would be 7y minus 3z equals negative 1. And we add. The z's cancel. I have 6y equals negative 6, and I can divide both sides by 6. Y equals negative 1. So I've solved for one of my variables. Now I'm going to plug the negative 1 back in to either equation that had just the y and z. I'm going to pick the one that has the star by it right there, no particular reason. So I'm going to plug that y in, negative 1 minus 3z equals 5. And then I can add 1 to both sides. Negative 3z equals 6. Divide by negative 3, and z is negative 2. Now I have y and z. I can go back to my original 3 equations and just pick any one of them, plug in the y and the z, and I can solve for x. I'm going to do the one that was on the very top of the original 3 equations, and I'll have x minus 3 times negative 1, and then the z was minus 2 equals 4. So that would be x plus 3 minus 2 equals 4. X plus 1 equals 4. X equals 3. Now I have my x, my y, my z, and those three numbers represent what's called an ordered triple. And it represents the intersection of three lines in three-dimensional space. X, Y, Z are three dimensions. You have straight left and right, you have straight up and down, and then you have straight forward and back, which would come towards you and go away from you. And so the three original equations, if they were graphed in three dimensions, they would all intersect at the point 3, -1, -2.